Welcome back to Fun Facts Online. Today we are stripping away the invisible layers of the world around us to look at a technology you likely use every single hour of every single day, yet probably misunderstand fundamentally. We are talking about Bluetooth, but not the Bluetooth you know, not the jagged audio connections of 2005 or the simple pairing of your smartwatch. We are diving deep into the newly released Bluetooth 6.0 and its game-changing feature called channel sounding. This is not just a software update. It is a fundamental shift in physics that changes Bluetooth from a tool for connectivity into a precision instrument for spatial awareness. For the next 20 minutes, we are going to explore how we are teaching our devices to understand exactly where they are in the physical world, down to the centimeter, and why this matters for the future of security, automation, and our daily lives. Let us start by understanding the problem. For over 2 decades, Bluetooth has been the invisible thread connecting our digital lives. It replaced cables. It created the Internet of Things. But for all its success, Bluetooth has always had a significant blind spot. It knew that devices were connected, but it had a very poor understanding of where those devices were relative to each other. Imagine talking to someone in a pitch-black room. You know they are there because you can hear them. But are they standing right in front of you? Or are they shouting from the other side of the room? Historically, Bluetooth tried to answer this question using a metric called RSSI, or Received Signal Strength Indicator. The logic was simple. If the signal is strong, the device is close. If the signal is weak, the device is far away. It is like judging distance based on how loud a shout sounds. While this makes sense in theory, in the real world, it is a blunt and often inaccurate instrument. Bluetooth operates in the 2.4 GHz spectrum. Radio waves at this frequency interact chaotically with the physical world. They bounce off concrete walls, creating multipath propagation, or echoes. They are absorbed by water, and since human bodies are mostly water, simply holding your phone in your hand versus putting it in your pocket can drastically change the signal strength. This meant that RSSI could only give us accuracy within 3 to 5 meters. It was useful for knowing if a device was in the same room, but completely useless for critical tasks like securely unlocking your car door. This lack of precision created a proximity gap. Furthermore, it was insecure. If I wanted to steal your car that uses an old Bluetooth key, I could perform a relay attack. I could amplify the signal from your key while you were sitting in a coffee shop, making the car think you were standing right next to it. The car would see a loud signal, assume proximity, and unlock. This is where Bluetooth 6.0 and channel sounding enter the picture. This new standard, released in mid-2024, moves Bluetooth from an estimation technology to a precision instrumentation technology. It promises centimeter-level accuracy and robust security against those relay attacks. So, how does it work? How do we turn a radio chip into a radar? To understand this, we need to look under the hood at the 2 distinct pillars of channel sounding, phase-based ranging, or PBR, and round-trip time, or RTT. These 2 methods solve different parts of the distance equation, and they work together in a fascinating way. Let's start with round-trip time, or RTT. This is the intuitive part. Imagine you are throwing a tennis ball at a wall and timing exactly how long it takes to bounce back to your hand. If you know the speed of the ball, you can calculate the distance. In the world of radio, the tennis ball is a data packet, and the speed is the speed of light. Light travels at approximately 300,000 kilometers per second. That is roughly 30 centimeters per nanosecond. To measure distance with any real accuracy using time, the clocks in the Bluetooth chips must be incredibly precise, capable of measuring nanosecond-level differences. RTT provides us with a coarse validation. It draws a circle of possibility. It tells the system, for example, that the device is somewhere between 4 and 6 meters away. It is reliable, and crucially, it is secure because you cannot cheat the speed of light. However, measuring time of flight alone is difficult to get perfect down to the centimeter without incredibly expensive hardware. That is where the second pillar comes in, phase-based ranging, or PBR. This is the star of the show for accuracy. PBR acts like a virtual tape measure. Instead of timing a pulse, it looks at the wave nature of the radio signal itself. Radio waves are sinusoidal. They cycle up and down. When a signal travels from an initiator, like your car, to a reflector, like your phone, and back, it arrives at a certain point in its cycle, its phase. If you change the frequency of the signal, the wavelength changes, and consequently, the phase at the point of arrival changes. By measuring the phase difference across multiple different frequencies, the device can mathematically calculate the precise distance the wave traveled. Bluetooth channel sounding uses up to 72 different frequency channels to gather this data. By hopping through these 72 channels, it gathers a massive amount of phase information, averaging out errors caused by noise or slight reflections. This allows PBR to act as a vernier caliper, pinpointing the location to within 10 to 30 centimeters. But there is a catch. PBR suffers from a problem called aliasing, or ambiguity. If the distance is too great, the phase cycles wrap around. It is like a clock striking one. You do not know if it is 1 p.m. today or 1 a.m. tomorrow just by looking at the hands. The device might calculate a precise distance, but it cannot tell if the object is 1 meter away or 101 meters away, because the phase looks identical. This is why Bluetooth 6.0 combines both methods. The synergy is brilliant. RTT draws the broad circle of possibility, confirming the device is roughly 5 meters away, not 105. Then, PBR steps in to measure exactly where within that circle the device sits, refining the measurement to 5.23 meters. This combination solves the ambiguity problem while maintaining high precision. Now, let's talk about the real-world environment. We mentioned earlier that radio waves bounce off walls and objects. This creates multipath signals, ghost echoes, that arrive slightly later than the direct signal. To combat this, Bluetooth channel sounding supports multi-antenna configurations. Devices can switch between up to 4 different antenna paths. If one antenna is blocked by your body, or confused by a reflection from a metal filing cabinet, the system can switch to another antenna to find a clearer line of sight path. It compares the phase and timing data from all combinations to filter out the bad paths and lock onto the true distance. All of this complexity happens in the new physical layer of the Bluetooth stack. To support PBR, the Bluetooth radio transmits a continuous tone, a pure, unmodulated sine wave, rather than the usual data packets. This allows for the cleanest possible phase measurement. The system utilizes 72 channels, compared to the standard 40 used in Bluetooth Low Energy, providing a wider bandwidth for better resolution. The specification defines 4 operational modes to give developers flexibility. Mode 0 is for calibration, synchronizing the clocks between devices. Mode 1 uses RTT only. This is fast and power efficient, perfect for applications that just need to know if a user is approaching, without needing pinpoint accuracy. Mode 2 is PBR only, which is precise but risky due to the ambiguity we discussed. It is mostly for controlled environments. And then there is Mode 3. This is the gold standard. It performs both RTT and PBR in a single procedure. This is the mode that will be used for high-security applications like digital keys. Speaking of security, this is perhaps the most critical advancement. We talked about relay attacks earlier, the man-in-the-middle scenario. Channel sounding effectively closes the door on this threat using cryptographic distance bounding. Because RTT measures the speed of light, it enforces a strict physical limit. You cannot cheat physics. If a thief relays the signal, their processing time and the extra distance the signal travels introduce a delay. Even a delay of a few nanoseconds is detectable. The system sets a distance bound. If the signal claims to be from 1 meter away based on the data payload, but the RTT shows a delay consistent with 50 meters, the lock rejects the request immediately. Furthermore, Bluetooth 6.0 introduces a metric called NADM, or Normalized Attack Detector Metric. This value analyzes the flatness of the channel response. In a clean environment, phase data follows a predictable pattern. In a manipulated environment where an attacker is splicing signals, the data looks jagged. A high NADM value alerts the system that an attack is likely in progress. Additionally, the sequence of frequency hops across those 72 channels is cryptographically randomized. Both devices share a secret seed, so an attacker cannot predict which frequency will be used next, making it impossible to jam or spoof specific tones in real time. So how does it stack up against the competition? You might be thinking of Ultra-Wideband, or UWB, which is currently used in Apple AirTags and some premium car keys. UWB is technically still slightly more accurate because it uses massive bandwidth pulses. However, UWB is expensive. It requires a dedicated secondary chip and consumes more power. Bluetooth channel sounding has a massive advantage: ubiquity. Bluetooth is already in 5 billion devices shipped annually. The upgrade to channel sounding is largely a matter of integrating it into the main system on chip that every phone already has. It follows the good enough principle. If Bluetooth CS offers 90% of UWB's performance for 10% of the cost and friction, it will likely capture the vast majority of the market. It is also far superior to Wi-Fi RTT, which is a battery hog, and 5G positioning, which is designed for outdoor macro tracking rather than finding your remote control under the couch. Let's look at the real-world applications, because this is where the technology becomes tangible. The killer app is the automotive sector. The Car Connectivity Consortium is already adopting standards leveraging this. Picture this. You walk up to your car. At 10 meters, the car wakes up using power-efficient MODE1 RTT to turn on the lights. As you reach for the handle, it switches to MODE 3. It cryptographically verifies you are exactly at the driver's door, not the passenger door, and definitely not inside the cafe across the street. It prevents lock-in accidents because the car knows if the key is inside or outside the cabin. Beyond cars, think about consumer electronics. Current Find My trackers rely on a mesh network to say an item is nearby, but you still have to ring it to find it. With channel sounding, your phone could show a compass-style interface saying, "Your keys are 2.5 meters ahead, slightly to the left." In industrial settings, this technology becomes a safety-critical tool. Forklifts equipped with initiators can detect workers wearing vests with reflectors. If a worker enters a 3-meter danger zone, the forklift can automatically halt. Unlike RSSI, which false alarms constantly in metal-filled warehouses, CS provides the reliability required for safety certifications. In museums, audio guides could trigger based on your precise distance to a specific painting. In hospitals, it can track if a doctor washed their hands for the required time by measuring the distance to the sink before approaching a patient. Of course, implementation is not without challenges. To get the most out of this, hardware needs to improve. Developers need to integrate antenna arrays, which take up board space and require complex RF design. The internal clocks, or crystals, need to be higher quality to minimize drift. There is also a significant complexity jump for developers. You cannot just ask the code for distance. You have to configure sub-event intervals, channel maps, and security thresholds. It requires a deeper understanding of RF physics. And while low power, phase-based ranging is an active radio process. Continuous ranging will drain batteries, so developers will need to implement smart duty cycling, perhaps using motion sensors to stop ranging when a device is stationary. Looking to the future, the ecosystem is just waking up. Bluetooth 6.0 was released in mid-2024. We expect to see the first compliant chips from vendors like Nordic, Silicon Labs, and TI hitting the market in 2025. By 2026, flagship phones and cars will likely integrate the technology, followed by mass adoption in consumer tags and tools by 2027. The long-term future lies in the combination of channel sounding and artificial intelligence. Raw phase and timing data is noisy. Machine learning models running directly on the Bluetooth chip will be able to learn the RF fingerprint of a room, distinguishing between a direct signal and a wall reflection better than any static algorithm. This could push accuracy down to sub-10 centimeter levels. In conclusion, Bluetooth channel sounding is a monumental step forward. It transforms our devices from being merely smart to being spatially aware. It replaces the flaky, insecure proximity estimations of the past with a system that is mathematically precise and cryptographically secure. As this technology permeates our world, the question our devices ask will no longer be, "Is it connected?" but rather, "Where exactly is it?" And for the first time, Bluetooth will have the right answer. Thank you for listening to G Fun Facts Online, and we will catch you in the next deep dive.